Hello everyone, this is lecture 17, linear dependent and linear independent. In this lecture, we're going to look at the concept of linearly dependent and linearly independent set of vectors. So in the last lecture, we looked at the concept of linear combinations, span set or span up a set, right? And use that information to gonna build up and write down the definitions of linear dependence and linear independence, right? So for the linear dependence or linear independence, we first need to show that the vectors can be written as linear combinations of other vectors. So let's example one kind of a revisit example for the linear combinations concept that we learned in lecture 16. So for this example, example one, the vectors v of the form 19, 10, -1 is in the span of S, right? So in lecture 16, we look at the definition of the span of a set, right? Which is the span of a set is also a set. And this set is the set of all the linear combinations of the vectors in S. Right, so by that definitions, vector V is in the span of the set S, right? And the set S is the set consists of three vectors. Let me say this is V1, V2, and V3. Right? And because we say that the vector v is in the span of S, so therefore v can be written as linear combinations of three vector v1, v2, and v3. So since v is in the span of S, v can be written as a linear combinations of v1, v2, and v3. So that means there exists a constant C1, C2, C3. That means there exist C1, C2, and C3 such that V equal to C times V1 plus C2 times V2 plus C3 times V3. Right. So you have this vector equations and you substitute the form of V, V1, V2, and V3 into these equations. You got this is 19, 10, -1 equal to C1 times 3, -1, 2 plus C2 times -5, 0, 1 plus C3 times 1, 7, -4. And we're going to obtain a system of three linear equations with three unknowns, C1, C2, and C3. Right. So we obtain a system of the form. Right. So we're going to write 3C1 minus 5C2 plus C3 equal to 19. Negative C1 plus 0C2 plus 7C3 equal to 10. And the last equation is 2C1 plus C2 minus 4C3 equal to -1. So with these equations, we're going to turn this into an augmented matrix and then use Python to help with the reduced row echelon form, right? So I'm gonna skip on the formality of doing Gauss-Jordan eliminations and just use Python to help with the reduced row echelon form. Let me turn to Python to help with the calculations. So here's the setup, here's the lecture note, here's the code. So hopefully at this point, you are familiar with this piece of code. So again, what we're gonna do is we're gonna turn this system into an augmented matrix, and we're going to put that augmented matrix into Python, and hopefully we're gonna obtain a reduced row echelon form. Okay, so the system or the augmented matrix of the system is 3, -5, +1, and +19. In the second row, we have -1, 0, +7, and +10. In the last row, we have 2, 1, -4, and -1. Right, hit Shift Enter, and it's going to give you this reduced row echelon form. And from this reduced row echelon form, so it's just going to write Python. We obtain that C1 is going to be equal to 4, C2 is equal to -1, and C3 is equal to +2. All right, so from here, we can explicitly write down the linear combinations of V. Right, then V is equal to 4 times V1 minus V2 plus 2 times V3. Okay, so again, V can be written as a linear combinations of V1, V2, and V3. In this case, C1 is equal to 4, C2 is equal to -1, and C3 is equal to +2. So again, V is written as the linear combinations of V1, V2, and V3. Actually, another way to look at this linear combination is that V depends linearly on V1, V2, and V3, right? Because V1, V2, and V3 are linear terms. Okay, so in that particular sense, we have something called linearly dependent, right? So V linearly depend on V1, V2, and V3. So this implies that V depends linearly on V1, V2, and V3. Okay, so in a way, you see the concept of linearly dependent or linearly independent in this particular example. So let's write down the definitions of linearly dependent or linearly independent. So a set S equal to V1, V2 to Vn is linearly dependent if there exist scalars. So exist scalars C1, C2 up to Cn. Not all are zero. Right, so there might be some zero for C1, C2, C3, something like that, but not all the scalars are zero, such that you have that C1, V1 plus C2, V2 plus up to Cn, Vn equal to 0 vectors. And we can see this particular equation from here, from this example, by rewriting this equation as for V1 minus V2 plus 2V3 minus V equal to 0. So you just basically move V to the right-hand side. Or rearrange the term so that we obtain the 0 vector on the right-hand side of the equations. All right, so because of this statement or this equation, we say that V1, V2, V3, and V are linearly dependent on one another. Okay. If this, and I'm going to call this equation star. So if star only holds for C1 equal to C2 equal to Cn equal to 0, right? If all of these scalars are 0, then the set S is linearly independent. And so that means they do not depend on one another. In the first case, the vectors depend on one another. In the second case, all the vectors do not depend on one another, not really depend on one another. So moving on to some example here. So I have the following set. I have the set of 1, 2, and 2, 4. So two vectors in R2, and they are linearly dependent. And as you can see from by looking at the two vectors, vector, let's say vector v1 is actually, or vector v2 is actually twice vector v1, or vector v1 is half of vector v2. Okay. Another way in to write this relationship is that v1 or c1 times v1 plus c2 times v2 is equal to a zero vector. Right? So you have -2 times 1, 2 plus 1 times 2, 4 is equal to 0 vector. So therefore, these two vectors, 1, 2, and 2, 4, are linearly dependent on one another. Eventually, we're going to learn how to find this values, this coefficients, so C1 and C2, so that we can write these vectors in the set as linearly dependent or as linearly independent. The next set that we're going to consider is the set of three vectors in R2. So the vectors are 1, 0, 0, 1, and -2, 5. So this set is also linearly dependent because we could be able to find the constants such that it can be written as C1 times V1 plus C2 times V2 plus C3 times V3 equal to 0 vector. So here you can be able to find the constant 2 times 1, 0, minus 5 times 0, 1, plus 1 times -2, 5 is going to be equal to 0 vector. So therefore, this set is also a linearly dependent set. In part C, in problem C, you have a set of 0, 0, 1, 2. And this is, of course, a linearly dependent because you can write 1 times 0, 0 plus 0 times 1, 2 equal to a 0 vector, right? So this particular coefficients can be anything really, because anything multiplied with 0 is going to be equal to 0, right? So it can be 2 times 0, 0, right? It can be -5 times 0, 0. Still, because you have this is going to be always 0 in the coefficient here, we can set that to be equal to 0 as well, so that the sum of this two vectors going to be equal to a 0 vector. Therefore, the set is a linearly dependent set. All right, so in the next example, we're going to see if the set in this particular, if the set is linearly independent or linearly dependent or not, right? So, in other words, we're going to find the value of C1, C2, and C3 such that C1 times V1 plus C2 times V2 plus C3 times V3 is going to be equal to 0 or not. So we're going to let these vectors V1, V2, and V3. All right. So to test for a linear independence or linear dependence, we form the equation that's C1 V1 plus C2 V2 plus C3 V3 is going to be equal to a 0 vector. So here you have V1, 1, 2, 3, V2 equal to 0, 1, 2, and V3 equal to -2, 0, and 1. So C1 times 1, 2, 3 plus C2 times 0, 1, 2 plus C3 times -2, 0, 1 equal to 0, 0, 0. Right. From here, you obtain a system of linear equations again, because there are, you have linear equations and 3 unknowns. Okay, so we obtain the system. Right, so C1 plus 0 C2 minus 2 C3 equal to 0. And the next equation is 2C1 plus C2 plus 0 C3 equal to 0. And 3C1 plus 2C2 plus C3 equal to 0. Now we're going to turn to Python to help with the calculations, right? We want to find the value of C1, C2, and C3. Again, if C1, C2, and C3 are all equal to 0, then you say that the set is linearly independent. If C1, C2, and C3 are different from 0, or some of that equal to 0 only, then you can say that the set is linearly dependent. All right, so I'm going to turn this to Python. What I'm going to do is to rewrite this system as the augmented matrix, input that into Python, and hopefully they give me something related to the reduced row echelon form. Okay, so let me turn to Python. So now the augmented matrix is 1, 0, -2, and the last entry is 0 as well. The second row is 2, 1, 0, and 0. The third row is 3, 2, 1, 0. Now hit Shift Enter, and this is the reduced row echelon form. And as you can see, you have that C1 is equal to 0, C2 is equal to 0, and C3 is also equal to 0. So from Python, we obtain that C1 equal to C2 equal to C3 equal to 0, right? In order, another name for this particular type of solution is called trivial solutions, right? Because all the variables are equal to 0. Right, so we obtain the trivial solutions. When we obtain the trivial solution for C1, C2, and C3, or the scalars, we say that the set is linearly independent. Right, so this implies that the set S is linearly independent. All right. So hopefully you got some idea of how the set, or how to determine the set to be linearly dependent or linearly independent. All right. So in the next example, we're going to look at the idea of linearly independent or linearly dependent set in terms of graphs. All right. So in part A, you have 2 vectors, 3, 1, and vector 6, 2. And as you can see, the vectors v2 is twice as the length of vector v1, right? So in a way, v2 is equal to 2v1. So that is v1 and v2 depend on one another. Okay, so notice that v2 is equal to 2v1. If you rearrange this particular equations, we can have that, or negative 2v1 plus v2 is equal to the 0 vector, right? So this shows that v1 and v2 depends linearly on one another. Thus, the set, if you have a set of v1, v2, is linearly dependent set, right? Or linearly dependent. All right. And as you can see on the graph here, vector v1 and vector v2 kind of light on the same light going through the origin, right? So they are linearly dependent. Now moving on to the second part of the problem. Now you have two different vectors, v1 equal to 3, 2, and v2 is equal to 6, 2. So this is v1 and this is v2. And graphically, you can see that these two vectors do not light on the same line, right? They are on different lines, right? So they are two different vectors going into two different directions, right? And we can say that v1 and v2 are not multiple of one another. That is, v1 and v2 do not depend on one another. Therefore, the set S of v1 and v2 is linearly independent. Right, so they independent from one another. All right. So from this example, this two example, we can write down kind of the characterizations of linearly dependent set, right? Or set of one or two vectors. So a set of two vectors, let's say a set of v1 and v2 is linearly dependent if at least one of the vectors is a multiple of the order. And you can see this in example 4a. Now, the second characterization is that the set is linearly independent if and only if neither of the vectors is a multiple of the order. And you can see this in example 4b. All right, so intuitively, right, the intuitive idea is that in geometric terms, two vectors are linearly dependent if and only if they lie on the same line through the origins. And of course, you see this in example 4a. Right, so example 4a. Right. So that's the relationship between linearly independent or linearly dependent set. And you see this for the case of two vectors. Right. Now, for the set of two or more vectors, how could you actually prove this kind of relationship? So vectors v1, v2, up to vn in Rn. Right, so you have n vectors in n dimensions, are linearly dependent if and only if at least one of the vectors can be expressed or can be written as a linear combination of the orders. All right, we're going to prove this particular theorem. Now, this is the case of a general, this is the general case, right? So it's set of two or more vectors. In this case, we kind of generalize that by considering n vectors in n dimensions, right? And we want to know if the vectors are linearly dependent or the set of this vector is the linearly dependent set, right? If that is the case, we will need to show that the set, one of the vectors in the set can be written as linear combinations of the other vectors, right? That's in the forward directions. Now in the backward directions, because we have if and only if statement. If one vectors can be written as linear combinations, can you actually rearrange these particular equations of linear combinations in term of the equation C1 times V1 plus C2 times V2 up to plus Cn times Vn equal to a zero vector or not? If you can, then that show it the vectors are linearly dependent. All right. So that so there's two parts to the proof. Right? The first one is the forward directions. That first we consider that these n vectors are linearly dependent when we use that statement to prove that at least one of the vectors can be expressed as the linear combinations of the other. Now the backward directions again is that first we assume that at least one of the vectors can be expressed as the linear combinations of the others. Then we arrange the linear combination equations so that we can obtain C1 times V1 plus C2 times V2 up to plus Cn times Vn equal to the zero vector to show a linearly dependent idea. All right, so here's the proof. So suppose V1, V2 up to Vn in Rn are linearly dependent. All right. Then by definitions, there exists C1, C2 up to Cn, not all are zeros, such that C1, V1 plus C2, V2 plus up to Cn, Vn equal to the zero vector. So this is from the definitions of linearly dependent or linearly independent concept. Now suppose again that you have C1 is different from zero, right? So this particular scalar is not going to be equal to zero. C2 can be zero, C3 can be zero, everything else can be zero except for C1, right? C1 cannot be equal to zero. And we choose this particular C1 or particular scalar. In mathematics, you have a term or a statement say without loss of generality. Because we can make these assumptions for C2, right? You can let C2 to be different from zero. You can set C3 to be different from zero. It doesn't matter, right? It's just convenient for us to prove that when you set C1 different from zero. All right, so we suppose that C1 is different from zero. So therefore, you can write C1 V1 to be equal to negative C2 V2 minus C3 V3, now up to negative or minus Cn Vn. Okay, So we just rearrange the term so that on the left-hand side, we only have C1, V1. Everything else we move to the right-hand side. Now, what we do next is we divided both sides for C1 because we make the assumption that C1 is different from 0. So the divisions is possible. Right? So now V1 is equal to negative C2 over C1. V2 minus C3 over C1, V3 minus dot 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 up to Cn over C1, Vn. Okay. Now C2 over C1 is right because C1, C2 up to Cn are constants. Therefore, the fraction C2 over C1 also a constant, C3 over C1 also a constant, and so on and so forth. Now, if you put an extra negative sign in there, is still a constant, right? The coefficients negative C2 over C1 is still constant. Negative C3 over C1 is still constant, so on and so forth. So this shows that V1 is a linear, or sorry, V1 can be written as linear combinations, as a linear combination of V2, V3 to Vn. Okay. So we just proved the forward statement. Okay. So we show that suppose you have n vectors are linearly independent, and therefore we can write a vector as a linear combinations of the orders, right? If you choose C2 to be different from 0, we can arrange, we can keep C2, V2 on the left-hand side and move everything else to the right-hand side. If we choose C3 to be different from 0, we can do the same game and keep C3, V3 on the left-hand side and move everything else to the right-hand side. All right, so that's the forward statement. So conversely, so let me move things around here. So I can keep Bn up here. So V2, V3 up to Vn. Okay. Now conversely, suppose V1 can be written as a linear combinations of the other vectors. Then there exist scalars C1, Cn, C2, C3 up to Cn, such that V1 is right. V1 now can be written as linear combination of the other vectors. So V1 is equal to C2 V2 plus C3 V3 up to Cn Vn. Okay. Now we rearrange these equations in a way that we get C2 V2 plus C3 V3 plus dot 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 up to Cn Vn minus V1 equal to 0 vector. Then this shows that V1, V2 up to Vn are linearly dependent. All right, so this is the fun proof one. So we just proved this theorem say that vectors, n vectors are linearly dependent if and only if at least one of the vectors can be expressed as linear combinations of the other vectors. All right. Now moving on to the next example. So in this example, we want to determine whether the set of vectors in M2 by 2 matrix is linearly independent or linearly dependent. So I have this particular set with three matrices or three 2x2 matrices. And I want to show, or I want to know if this set is linearly independent or linearly dependent. Okay, so again, we're gonna use the definitions of linearly independent or linearly dependent set to prove this particular example. All right, so from the equations, you have C1 V1 plus C2 V2 plus C3 V3 equal to 0. We have, right, so even those are matrices, we're just going to follow the vector equations for now. So V1 is going to be equal to this matrix, V2 equal to this matrix, and V3 equal to this matrix. So we get C1 times the matrix 2, 1, 0, 1 plus C2 times the matrix 3, 0, 2, 1 plus C3 times the matrix 1, 0, 2, 0 and equal to the right hand side in this case because we are considering the 2x2 matrices. So the right hand side should be a 2x2 0 matrix, 0, 0, 0. Okay. Now from here, we're going to obtain a system of linear equations. All right. Now, we're going to consider combining the component wise of the equations. So 2C1, right, plus 3C2 plus 1C3 equal to 0. Right. So we obtain the following equations, system of equations, it's just system. So again, 2C1 plus 3C2 plus C3 equal to 0. So that's the first equation corresponding to the first component of the matrices. Right? Now for the second component, you have 1 times C1. So C1 plus 0 C2 plus 0 C3 equal to 0. So C1 plus 0 C2 plus 0 C3 equal to 0. Now for the third equations is coming from this entry. So 0 C1 plus 2 C2 plus 2 C3 equal to 0. So 0 C1 plus 2 C2 plus 2 C3 equal to 0. And the last equation coming from 2C1 plus 2C2 plus 0 C3 equal to 0. So C1 plus C2 plus 0 C3 equal to 0. Now again, we can solve this by hand or we can utilize Python to help with calculations. So I'm going to turn this system into an augmented matrix, plug that into Python, and they're going to give me some answer for C1, C2, and C3. All right, let me turn to Python now. So this system, we're going to turn this into augmented matrix of the form 2, 3, 1, 0. That's for the first equations. The second equation is 1, 0, 0, 0. The third equation is 0, 2, 2, 0. And we need the fourth row or the fourth equation as well, which is going to be 1, 1, 0, 0. Now shift enter, and we're going to get the following reduced row echelon form. And it shows that C1 is equal to 0, C2 equal to 0, and C3 equal to 0 as well. So from Python, I get that C1 equal to 0, C2 equal to 0, and C3 equal to 0. Or we obtain trivial solutions. Right. Because we obtained trivial solutions for C1, C2, and C3, we say that the set, so this shows that the set S is linearly independent. Right. Gonna move on to the next example. In this example, we're going to look at this following set of vectors or this column vectors. Because we have 4 rows in 1 column, so it's considered column vectors. Okay, so we have 4 vectors. We want to know if this set of vectors is linearly independent or linearly dependent. So the setup is going to be the same, right? From the equations, C1 V1 plus C2 V2 plus C3 V3 plus C4 V4 equal to 0 vectors, right? So this is V1, this is V2, this is V3, and this is V4. All right, so you have these 4 vectors going to plug into this vector equations. We get, right, that C1 times 1, 0, negative 1, 0, plus C2 times 1, 1, 0, 2, plus C3 times 0, 3, 1, negative 2, plus C4 times 0, 1, negative 1, 2, equal to a 0 vector. So in this case, you have a column vector, so it's going to be 0, 0, 0, 0. And from this vector equations, we're going to obtain the system of linear equations. So we have 4 entries of vectors. So this is going to be 4 linear equations in the system. So we obtain the system of the form that C1 plus C2 plus 0 C3 plus 0 C4 equal to 0. That's the first equation. And this equation is obtained from the corresponding entry, which is the first entry here. So C1 times 1, which is C1, plus C2 times 1, which is C2 here, plus 0 C3 plus 0 C4 equal to 0. Now the second equations corresponding to the combinations of the second entry of the vector. So 0 C1 plus 1 C2 plus 3 C3 plus 1 C4 equal to 0. So 0 C1 plus C2 plus 3 C3 plus C4 equal to 0. And so on and so forth. So the third equation is negative C1 plus 0 C2 plus C3 minus C4 equal to 0. And the last equation is 0 C1 plus 2 C2 minus 2 C3 plus 2 C4 equal to 0. Now, again, we're going to turn to Python to help with the calculations. So we're going to turn this equation system into an augmented matrix and plug this into Python. So the first row is going to consist of the coefficients 1, 1, 0, 0, and the last entry in this row is 0 as well. The second equations, the entries are 0, 1, 3, 1, and the last entry is 0. The third row is negative 1, 0, 1, negative 1, and 0. And for the last equations, the entry of the coefficients are 0, 2, negative 2, positive 2, and 0. All right, so we're gonna hit Shift Enter, and this is the reduced row echelon form, and you can see that C1, C2, C3, and C4 are equal to one another and equal to 0 vector, which is that we obtain the trivial solutions. So using Python, we obtain the trivial solutions. we obtain trivial solutions for the system. That means the set S is linearly dependent. Linearly independent. All right. So we're gonna move on to the last example in this lecture. So in this example, we have a set of polynomial functions of degree 2 or quadratic functions. The set consists of 3 vectors, 1 plus x minus 2x squared. The second vector is 2 plus 5x minus x squared, and the last one is x plus x squared. We want to show that this set is linearly dependent, right? And we're going to use this information of linearly dependent to rewrite one of the vectors in the set as a linear combinations of the other 2 vectors. All right, so again, the setup is going to be the same, right? We just change the form of the vectors in the set. All right, so form from the equations. C1 V1 plus C2 V2 plus C3 V3 equal to 0, we get, right? So the vectors now, V1 is going to be this, right? V2 is going to be this, and V3 is going to be this. All right. So we get C1 times 1 plus x minus 2x squared plus C2 times 2 plus 5x minus x squared plus C3 times x plus x squared equal to 0. Okay. Or in this case, because we consider a polynomial function of degree 2, technically, the right-hand side should be 0 plus 0x plus 0x squared. Right. So that's for later, right? We need this particular form for later, but because 0 plus 0x is going to be 0 plus 0x squared still is going to be 0. So we're going to write this just 0 for now. Right? We're going to keep this form for later. So 0 plus 0x plus 0x squared for later. Now, what we're going to do for the left-hand side is that we're going to distribute C1, C2, and C3 into the parentheses, right? And then we're going to combine like terms. So distribute C1, C2, and C3, we get C1 plus C1x minus 2C, let me be careful here, C1 times 2x squared plus C3 or 2C2 plus 5C2x minus C2x squared plus C3x plus C3x squared equal to 0. Now combine like terms. So x squared together, so x squared here, right? And then, or rather we factor x squared. When we left with negative 2C1 minus C2, so thing related to x squared, right? Or we factor x squared minus C2 plus C3. Now we factor x. So the terms related to x are C1x, 5C2x, C3x. You got C1 plus 5C2 plus C3. And a term that by itself without any x attached to it, you have C1, 2C2, and that's it, right? So you get plus C1 plus 2C2 equal to 0. All right. Now you're going to match the coefficients on both sides of the equation. So remember this particular form of 0 that we have earlier. So let's replace that here. Let's move it over here. Right. So what do I mean by matching the coefficients on both sides of the equation? So this for x squared, this is the coefficients, right? And it match with the 0 on the right-hand side, the 0 that attached with x squared. Now for the coefficient of x, this is the coefficients. It's get equal to the coefficients of x on the right-hand side. And this is the coefficients by itself without any x attached to it. And you set that equal to 0, right? With the 0 on the right-hand side by itself. Okay, we obtain the following system. Right, so that is negative 2c1 minus c2 plus c3 equal to 0. c1 plus 5c2 plus c3 equal to 0. And c1 plus 2c2 plus 0c3 equal to 0. Now you have a system of 3 linear equations with 3 unknowns, c1, c2, and c3. We're going to use Python to help with the calculations of C1, C2, and C3. All right, so the augmented matrix of this system is, so let me delete a few things here. So we just need 3 equations for entry in each row. So the entry in the first rows are -2, -1, +1, and 0. The second row is 1, 5, sorry, 5, 1, and 0. And the third row is +1, +2, 0, and 0. All right, hit Shift Enter. So it's a little bit different from the last few examples that we have. In this case, the reduced row echelon form not going to give you trivial solutions. In fact, going to give you some solution, right? Some solution that is different from zeros. We call that the non-trivial solutions. All right, so from using Python, we obtain that C1 minus minus 2/3 C3 equal to 0, and C2 plus 1/3 C3 equal to 0. So from here, you can solve for C1 and C2 in terms of C3. Or C1 equal to 2/3 C3, and C2 is equal to -1/3 C3. Okay. So since we obtain non-trivial solutions, of C1, C2, C3, we show that S is linearly dependent. All right. So there is a third, the second request to this problem that also show that one of the vectors, the set in the set, can be written as a linear combinations of the other two. Okay, so first we show that the set, the given sets, is linearly dependent. Now we're gonna manipulate the informations that we get for C1, C2, and C3 to write one of the vectors in turn as a linear combinations of the other two vectors. All right. So since C1 equal to 2/3 C3 and C2 is equal to -1/3 C3, C3 in this case calling a free variable. Okay. So we make a quick note here. So that is we are free to choose the value of C3. Sorry, C3, not V3, C3. All right. So because we are free to choose the value of C3, we say that let We can let C3 to be 3 in this case. Why 3? It can be anything really. It can be 9,000, negative 1,000, something like that. But we choose 3 in this case so that it's easy to do the calculation for C1 and C2. Right. Usually we let C3 equal to T for T is any real numbers, and we can solve for C1 and C2 in terms of T. But here we want to write one vectors as linear combinations of other two vectors. We want to specifically give a value for C3. Okay, so here, because for convenience of calculations, we're gonna let C3 equal to 3. Then C1 is equal to 2 and C2 is equal to negative 1. Then we get, that so 2v1 minus v2 plus 3v3 going to be equal to 0 vector, or rather v2 is equal to 2v1 plus 3v3, right? So we just move negative v2 to the other side. All right, so v2 in this case in the set is the polynomial of the form 2 plus 5x minus x squared. 2 plus 5x minus x squared equal to 2 times 1 plus x minus 2x squared plus 3v3, which is x plus x squared. Now, if you expand the right-hand side, you get 2 plus 2x minus 4x squared plus 3x plus 3x squared. You're going to obtain, right, so 2 plus, so 2x plus 3x going to be 5x, and negative 4x squared plus 3x squared is going to be negative x squared. So we rewrite v2 as a linear combinations of v1 and v3, and the polynomial functions can be written as linear combinations of the other two polynomial functions. So that's it for me for this lecture. So in this lecture, we look at the concept of linear dependence and linear independence. The set is linearly dependent if there exists some scalars C1, C2 up to Cn, not all are 0, such that we have this particular vector equations. Right? And if this equation only holds when C1 equal to C2 is equal to Cn equal to 0, or you obtain the trivial solutions to these scalars, then the set is linearly independent. All right, so that's it for me. Please let me know if you have any questions. Thank you.